Hi everyone, this is Shaunak Vyas. Today I am going to demonstrate the Modbus RTU function subset implementation in Cypress PSoC5. For my experiment, I have used Cypress Semiconductor prototyping kit for PSoC5, which is known as CY868059. As you can see here, it can be directly plugged with the PC using the USB port. The kit's link that describes all its features and all the documentations and its relevant softwares is given here. If you click here on my blog, you will get redirected here. About Modbus, if we say it's a data communication protocol widely used in industries. So if you click this particular link that I have shared, you will get redirected to the Wikipedia page of Modbus. You will get all the details regarding this. Also, I have referred a very good documentation regarding Modbus that I used as a reference for the entire project building, which is also shared here on the blog. As a part of the Modbus subset functions I have implemented 8 functions listed here. Modbus RTU has 16 functions. Out of them, 8 commonly used functions are implemented in this project. For testing all these functions that I have implemented on PSoC5, I have used a Modbus Master Tool called qModbus. If you click here, you will get redirected to this download of qModbus, which is an executable file that will be able to run in Windows. If we say about the programming method that I have implemented, I have used 64 coils, that is 60 bits of data, 64 discrete inputs, that is again 60 bits of data, 64 input registers which are each of 2 bytes, that makes 128 bytes of data, 64 holding registers that makes 2 bytes each, so it again makes 128 bytes of data. Uh, you can increase these numbers as per the memory capability of the microcontroller. I have used this particular number just to understand the philosophy of Modbus responses and queries. EEPROM is stored. EEPROM basically is used to store the values over power cycle. So the beauty of this project is that I have created a Modbus RTU function subset C library that can work on other microcontrollers as well, not just PSoC5. And the main.c file, if it gets understood and implemented properly, then this subset C library, Modbus subset C library, can easily be integrated with that. For the development purpose of the project, I have used the PSoC Creator 4.4 IDE. I am specifically giving the version of the IDE here because I have shared the code here, as you will be seeing. And in Cypress Semiconductors IDEs, what happens is if the version compatibility is not there, then chances are high that the code may not get built or some errors may come. So make it sure that you have this PSoC Creator 4.4 IDE while you want to work with this particular project. So the link is open now. You can download it. So while it starts getting downloaded, let's just connect the PSoC5 kit. So now we'll open the device manager. As you can see, there is no COM port available this time around. If we connect the PSoC5 kit, the COM port of it is available for us now, which is known as kit probe USB UART. My COM port is indexed as number 1. So let's see where our downloaders arrive. So we'll save this particular file at some temp folder. And we will extract it because it's a zip file. So now if you see over here and open the folder, you will have .cydsm folder in which you will get two files which are called modbus RTU.c and modbus RTU.h, which are the library files for the project. There is a main.c file. So these three files are the most important ones as far as this project is concerned. So let's just open the PSoC creator. So as you can see, I went to File section, then Open Project Workspace, and open this .cywrk file, which is a workspace file for the project. First thing we will do is we will be building the project. So we will go with the project, right click and clean and build. So while it gets built, we will go to connect, have an establishment of our PSoC5 with the IDE. So we'll go in the debug section to select debug target, PSoC5LP selection, OK/connect. So now it's connected. It is also built as we can see. Now we can directly program it from here. So now it got programmed. If you are having a fresh PSoC5 kit with you, the first thing that you will notice is your blue LED will get on, which indicates that the parameters that I already described in, like coil, input register, holding register, and discrete inputs are now initialized with some fixed values, and they are also written in the EEPROM. This is only a one-time thing. Once the EEPROM gets written, there is a flag set, and thereafter it doesn't get initialized. So as you can see in the main.c file, I have three functions relevant to EEPROM, which is initialize EEPROM, read EEPROM, and update EEPROM. So initialize EEPROM means we are setting up some standard values with the parameters, and we are writing them to the EEPROM using the update EEPROM function. Now it's about time to go to the qModbus tool. Serial port, you have to select kit probe USB UART as I have selected here. Baud rate is going to be 9600. Data bits is going to be 8. Stop bits 1. Parity none. Slave ID as I have set as 1. If you want to change the slave ID of your controller, you can go to the Modbus RTU.h file and get it changed over here. You can write any value in between 1 to 247. So now we will be reading the values. Let's say the first function is, so basically all the 8 functions that I listed on my blog, all these 8 functions that I listed here are there in the qModbus that we are going to test. So as you can see, the FF has come because it's a standard value. We can go with a 0 write with a write single coil function and writing a 0 over there. That means the first bit is going to be 0. Again, if we read, as you can see, the value has changed from FF to 7F now. Let's just keep it this way. We will check over power cycle whether this value gets retained or not. Read discrete inputs from 0 to 8 again. Again, we are getting the FF because it's a default value. Reading holding registers we are doing. We'll just read a single register as of now. It's a 2-byte value, so we can see basically this is the standard response frame from the slave which you will be getting to understand in this particular document that I have shared. Also, there are so many online helps available to understand Modbus. Read input registers. Again, it's AA55 we have set as default value. Write single coil we already done. Write single register. So let's say the value of the start address is 1. This is a holding register. It is having 16-bit value. Let's write 255 here. That means it will make a value of something like 0x00FF. Write multiple coils. So again, we will take as 8 as a reference and we will be writing 4 values here. We will be writing all zeros. Send. Now if we see read coils and we read from 8 start address to 8 coils, we can read 0F. That means first 4 bits are 0 as we set them. So this is also working. Write multiple registers. We can go with something like starting from 3 to 2 registers. Values are 255. Let's say here 254. Send. So now we have set all those things. We also have exception responses for each and every function. For example, in write single coil. For example, in write single coil, if you try to enter the start address as let's say 64, the start address basically starts from 0 and ends at 63 in our code because we are having only 64 values. So this is going to throw an error exception, as you can see. So this particular data frame that you are seeing right now is going to be understood better in a better way by referring that document that I have shared. So we have two kinds of error responses as of now. One is for the start address limitation, which is having the 63 as the highest one, and the second one is going to be right multiple coils. If we say start address can be, let's say, 55 and number of coils is, let's say, 10. This value, the summation of these two values should not exceed 64, because if we exceed 64, then again it violates our principle that we are going to use only 64 coils. So it is going to throw us an error exception. So this is how the system works. Now we will close this qModbus. We will disconnect the kit probe. As you can see in the device manager, it got disconnected. We will reconnect it. Now it came. We will again go to qModbus and we will check out the values that came. Let's say read coil 0 to 8. Yes, we got 7F. It's not FF anymore because we wrote the first bit as 0. We will go to the reading holding registers. We'll go with 2 to 4 registers. As you can see, we had 254. This value is making 255. This is making 254, which we set previously, which was from 1 to 2. So now the EEPROM is also working. So this is how the system works. If you want to see this blog that I am currently showing you right now, the link is given in the description of the video itself. I will be glad if you give me the feedback of my work by contacting me and giving me your valuable feedback, questions, comments and suggestions and submitting over here. I already shared my email ID with you so that you can contact me directly for further queries. Thank you so much.